This is Physics 2211 Lab number 2. The purpose of the lab is to observe the motion of an object that falls straight down dropped from rest. This is to see how the force of gravity and the drag effect affects the object's velocity and position. We will go over physics concepts behind the scenes, experiment and model setup, data analysis of the video, and comparison. The physics concepts and principles of this lab is based on Newton's second law, which states that the change in motion or the acceleration of an object is directly proportional to the force applied. This statement is the equation net force is equal to mass times acceleration, which is equal to the change in momentum over time, or mass times the change in velocity over time. We can calculate our net force through a free body diagram here, which we show that there's two forces, a force of gravity that is pulling it downward and a force of drag that is pulling it upward. Once we calculate our net force, we can put this into our velocity update formula over here and calculate our velocity at different points in time. When we calculate our velocity at different points in time, we can put this in our position update formula to do the same for position. We have two different models that we have for our lab. We have a gravitational model that assumes that there's no drag, which is net force is equal to the force of gravity, which is equal to negative mass times g. G is the acceleration due to gravity on Earth, which is equal to 9.81 meters per second squared. This is calculated through our force of gravity equation, other force of gravity equation. We also have a gravity that includes drag in our model, which is equal to net force is equal to force of gravity plus force of drag. Force of drag is equal to negative b times velocity squared times unit vector v. Our b is a proportionality constant, which basically shows how much drag that there is on our object. The results of our lab will give us the y position over time from the ball starting at rest at different points of time using our tracker software. We compared this to both of our models, the one with gravity and the one with drag. Our system is our paper ball, and our surroundings is the air resistance, which is our drag force, and gravitational field. Our initial conditions is that Vy is equal to 0 because the ball is dropped from rest, and our position is at 1.8 meters initially. We're going to record our video, we're going to track our ball positions over time, we're going to create our computational models, we're going to create graphs and compare all these graphs and draw conclusions. This is our video. The length between each frame you can see on the right grows bigger due to the acceleration increasing the velocity over time and the position downward. The initial conditions of our computational model are as shown. In line 36, we have our mass of our ball, which is arbitrary because the mass will cancel out. And in lines 39 and 40, we put our initial position and initial velocity according to the tracker. In line 44, we do the same with the time step. In line 49, we put the magnitude of the acceleration due to gravity, which is 9.81. Setting up our gravitational model, net force is equal to the force of gravity here. As you can show that net force is equal to negative mg. And then we put our velocity update formula and our position update formula as accordingly. B constant is equal to 0 because drag is not applicable. When we were setting up our gravitational with drag model, however, we have to include drag and we have to include a B. Our B is a proportionality constant we calculated through guess and check, and a higher B is more drag force that is on the object. As you can see here, FF net in our glow script is force of gravity plus force of drag. And we put this in our velocity update formula and our position update formula for it to update accordingly. These are our three graphs in comparison of position over time and velocity over time. From our left to right, we have our model with gravity only, our model with drag, and our experimental model. As you can see with the model with gravity only, it reaches higher magnitude of velocity in the same time period without drag. You can see this in our combined graph with the position over time. As you can see, the yellow one is down further. This shows that it falls faster than our experimental and a drag model. We fit our constant b to fit our experimental, but there's not that much discrepancy between all of them because the time interval is so short. The difference, though, is because of F drag decreasing the net force that accelerates it downwards. It decreased the net force that pulls it downwards, and we can put that in our velocity update formula to show that our velocity is lessened due to force of drag. Some possible errors is that the ball is moving in the x direction at time. There might be some external wind that decreases its y direction down. The ball may have bounced back slightly at the end, skewing the results a little bit. Human error in tracking it properly, and the tracker software is unable to be 100% exact. When we're asking our questions about what does it mean and which models, if any, predict a terminal velocity refers to when velocity reaches a constant when F net is equal to 0, which means it goes at a constant velocity. Without drag in our first model, no other force is opposing gravity, so that's not possible. It's going to continue to keep going downwards. This is only possible with the model that's with drag. In our free body diagram here, we have F of drag that's pulling up and force of gravity going down. When velocity reaches a certain point, F of gravity is going to equal to F of drag. As you can see from our velocity versus time graph on the right, it will approach an asymptote over time when velocity reaches a certain point. What if the object was initially thrown downward would the terminal velocity be the same or different than if it was dropped from rest? Throwing it downward will cause there to be initial velocity. However, the terminal velocity will be the same whether or not it was dropped from rest or if it had initial velocity. This is because the drag force is reliant on the velocity, and we're going to find a velocity that makes it so drag force is equal to the force of gravity. And it will probably reach the terminal velocity faster than if its initial velocity was 0. But as you can see from our two graphs, it reaches the same point. It reaches the same constant and the same velocity in our asymptote.